And the ways to do that were where it was to create obstacles for certain things to be able to move on certain planes in certain directions. What were those things that we wanted to create obstacles to? Do you remember what they were called? Dislocations, right. You needed to create obstacles to dislocation. And the first method was using point defects. Do you remember what those were called, what those defects were called? Yeah. Well, the vacancies is a point defect, and that was the first point defect we talked about, but it doesn't cause, it's not an obstacle to dislocation. There was another kind of point defect that was an obstacle to dislocations. Do you remember what that was?
Substitutional?
Substitutional was one type of them. There were two different types of them, and they were impurity atoms. And there were substitutional ones, and there were interstitial ones. So point defects were impurity atoms that were obstacles to dislocations. And the process, the engineering or manufacturing process, that one of them that adds defects was carburization. And we did some examples of that. But in general, the mechanism that uses point defects to strengthen is called solid solution strengthening. All right? The second kind of defect was a line defect. Do you remember what it was called? This is the one that maybe caused a little bit of confusion because these were obstacles to dislocations, and they were dislocations. A dislocation is a line defect, and dislocations are obstacles to one another. So if we could add to the number of dislocations, adding to the number of obstacles, we can make a metal stronger. And what was the process for adding dislocations? Do you remember? It caused the material to get brittle as it strengthened the material. Is that all? Okay. We had a couple of graphs that had on the x-axis this process, this percent something. Cold work, right. So cold work is this mechanism for adding line defects or dislocations. The formal name for that strengthening mechanism is strain hardening. So we got solid solution strengthening, that's adding point defects. Some people just call it alloying. And then there's strain hardening, that's adding line defects by doing cold work, by deforming. It has the downside of making a metal more brittle. And then the third kind of defect, which is what we'll talk about now, are surface defects. So we had one-dimensional point defects, two-dimensional line defects, and now we have three-dimensional surface defects. And they're not the surface of the metal, although that is sort of a defect. They're inside within the metal. So imagine that I've got my liquid metal and I'm letting it cool, and at certain points within the metal, it starts to solidify, like little seeds start to form and grow. And these crystals, these metal crystals, are growing in the liquid, in the molten metal. Now they're not clear like we kind of think of as crystals. They're opaque just like a metal is, but they have a crystal structure that's repeatable in 3 dimensions. And so they grow from their centers out until they bump into one another. And there's no longer any liquid metal, right? And there's a place between each of these that's a mismatch. That's a place where all of those surface atoms on the one crystal are missing a bond, and all the surface atoms on the neighboring crystal are missing a bond. And so So this might be one crystal, and of course, I'm just looking at this in 2 dimensions. And this might be the neighboring. Crystal, and there's that space in between and that mismatch place, right? And we know that dislocations move because we'll have atoms, we'll have that row of atoms that are missing a bond below. So that's a dislocation, and a dislocation moves when we apply a shear stress. And so this dislocation, right here, that row of atoms into the board, each of which is missing a bond. When this stress gets big enough, this bond breaks, and that bond forms, and everything kind of shifts. And then this bond breaks, and that bond forms, and everything sort of shifts. And this can happen because it's only one bond at a time that's breaking and forming. But once it gets to this point, there's my extra, it can't go any further because it's reached this border between 2 different grades, this grain boundary. So the grain boundaries, which aren't really lines, they're like spaces that don't have the right number of atoms. Wherever they are, if there's deformation happening, it stops. And remember we talked last time about resolved shear stress, and there will be one set of planes and directions where deformation could happen. Well, when we get to this place, there's still the stress right here, but maybe it just has to get bigger before it could activate this dislocation to start to move on this plane. So I have this dislocation that's moving on that plane. It reaches a boundary. Now the stress has to go up in order to be high enough to cause that dislocation event. Stress has to go up in order for it to have deformation. That means it's stronger. So these grain boundaries are dislocation obstacles. And if we can add to the number of grain boundaries, we could make a metal stronger. Just like adding point defects and adding line defects. All right, so let's say I have this thing, metal with 1,000 grains in it. And each grain has a boundary. How do I get more boundary? If I have a certain amount of volume, do I go somehow from 1,000 grains to 2,000 grains? Would that have more boundary, or would going from 1,000 grains to 900 grains have more boundary? So Jack's thinking if I go to 900 grains, I've decreased the number of grains, same volume, will that decrease or increase the boundary between them? Maybe let's think of it this way. I've got 10 grains in a certain volume, right? And if I go to 9 grains, same volume, those grains are going to have to be bigger, right? So I've got 9 larger grains. I'll have less boundary. As the grains get bigger, and there are fewer of them, or vice versa, as there are fewer grains and the grains get bigger, there's less grain boundary. So the way to add grain boundaries is to increase the number of grains, is to have grains get smaller. Are you with me? All right, so if I want more grain boundaries, to make the metal stronger, then I would have to decrease the grain size with more grains. One or the other. If I can decrease the grain size or if I can add more grains, either has the same effect. There's more grain boundaries. But that decrease grain size with more grains. All right, now think about soap bubbles and dishwater. Do the bubbles ever get smaller? No, typically they combine with other bubbles and they get, on average, larger. Over time until at some point you've got one large bubble. Yeah? That's thermodynamics. You can't make crystals get smaller thermodynamically. They won't, there's no way to make grains get smaller. There's no way to make soap bubbles get smaller. Everything's seeking to reduce its energy by increasing its surface area. All right? So, well, theoretically, we can make metals stronger by creating more grain boundaries, which results from somehow making the grains get smaller, but they would never, ever get smaller. If you apply heat, they get bigger faster. If you don't apply heat, they get bigger slow, but they never get smaller. So this can't be a one-step process. We can't deform like we do to make metals stronger. We can't just add an alloying element. In this case, we have to do 2 things, one at a time, in order to result in smaller grains. So this is what we have, how we increase strength via decreasing grain size, and the process is called recrystallization. Because he can't make grains get smaller, the only thing you could do is somehow cause new grains to form, new small grains to form and take over. In other words, you need to recrystallize. So the method so let's say I have a metal, let's say grains are about this size. And I've got 2, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7 grains. If I just heat, right then, what happens is what's called, kind of obviously, grain growth. And so I end up maybe with fewer grains, bigger grains, less grain boundaries. So adding heat to a metal, among other things, causes the grains to grow. And what would that do to the strength? If I make fewer grain boundaries, and we know grain boundaries add strength, then I'm decreasing the strength.
Brittle?
What was that?
Brittle?
Where did that come from? Yeah, what did you say?
Brittle?
No, making it brittle is deforming. If anything, we're making it softer. And you'll see that in a second. So if we just heat, we have less grain boundaries, it's softer. This is a process called annealing. Okay, if instead of doing that, we add cold work. So that could be drawing it or rolling it, but we end up with might be bigger than it ought to be. What happens to the strength when I cold work?
It increases.
What happens to the ductility?
It decreases.
We just did that. So if we just take this and we add cold work, we get increased strength because of all those dislocations and decreased ductility. That was our cold work process. If we were to describe the structure, these grains are called equine, meaning the same, axes, meaning they're approaching spherical. After cold work, I have elongated grains. So step one in this process is cold work, which we're familiar with. Then, after cold work, we add heat. First thing that happens is called recovery. And after recovery, everything will look just the same as it did. No physical, say, no change to grain size or shape. This would be the step of annealing when we were doing those examples of cold work and trying to get it down to a certain size. And we would have to anneal so that we could do more cold work. That's kind of like what happens here. There's a reduction in the number of dislocations. If we continue to heat, then we go through the process of recrystallization. The first part of recrystallization, that first part is called nucleation. A new set of strain-free heat-waxed grains are formed at highest energy locations. So we have these grains that and those grains have these new strain-free grains form at high energy locations. Highest energy locations are places where 3 grains coming together. Remember that this is a three-dimensional, two-dimensional image of something in 3 dimensions. So they might be coming together in and out of the board. Let's put some here. There's no magic about where I put them other than that we make sure to put them near where there are, where there's more than 2 grains put together. So step 1 in recrystallization is called nucleation. Step 2 is called grain growth. And during grain growth, the small, low-energy grains consume the large, high-energy grains. So we're decreasing in the amount of old material and increasing in the amount of new material. New material being low stress, low strain. And I'm apologizing, this whole thing is a bigger, like zoomed in. Let's make this portion of the would be, I think maybe you can see this, but on average, there's a less of the old material, the new material is taking over. And it's all the same metal, but when I say new material, I mean that metal in a less grained state. And so the average grain size is decreasing. And this continues, this grain growth continues until there's no old deformed grains. And let's see, 1, 2, 3, 4, 5, 6. Now it's going to maintain that shape, so. Grain growth is over when there's no strained material left. Recrystallization is over when we reach this point where there's no strained material left. So no, we call this grain growth, we also call this grain growth. And in this kind of grain growth, large grains grow. At the expense of small grains. So the average grain size is increasing. This kind of grain growth, the average grain size is decreased. And that's only because it's a whole new set of grains. But they're both called grain growth. One being as part of recrystallization. And throughout all this, we're heating. And that's the thermal energy that's driving this transformation. So when recrystallization is over, if we continue to heat, then we get the other kind of grain growth. Here, they say strength drops faster because throughout all of this, the strength is dropping. But once we finish recrystallization, then it starts to drop faster. When we reduce the number of dislocations, we reduce the strength. Throughout this process, probably the strength is staying relatively constant, but it's not going up. And here, it drops fast. So how would I demonstrate that? So if I say, this is my baseline strength of my, well, let me make it up so high. If this was my baseline strength before I did the process, solid solution strengthening is going to increase my strength. The extent of the increase is related to the percent of that impurity atom that I'm adding. So I could get, any increase in strength depending on concentration of the impurity atom. And there's a limit, right? I mean, there's a limit to how much you can get. Strain hardening, I can get the biggest increase in strength. Recrystallization will give me an increase in strength, but not nearly as big as the other two. So one of the parameters that helps you decide if you're going to try one of these three ways to strengthen your metal is how much you're going to get out of it. Solid solution strengthening is probably the most expensive way to do this. Right? Alloying requires a lot of heat, furnace energy. It requires another material. So it's probably the most expensive. But with solid solution strengthening, I could just make a stock of material from which I machine my parts. As far as hardening the surface, if I just need to harden this surface, well, this is the best way. When would cold work or strain hardening, when would that be the best option? When would it not matter that I'm losing ductility? Application where ductility isn't important. Better strength is really valuable. Anything in compression. Yeah. I just need to make sure this component that I'm using cold work to strengthen isn't going to be in bending, isn't going to be in torsion, isn't going to be seeing impact. Because brittleness will be a problem there. But it could be pretty easy. I mean, rolling a piece of steel isn't that difficult. It could be relatively easy to do this method. Recrystallization, that's a time-consuming, heat-consuming method, but that's it. And I end up with a material that's ductile. So I might need to change the strength. Okay, I'm doing cold work anyway. I might need to change the size. I'm doing cold work anyway. But I can't have brittleness. Okay, well, we'll recrystallize after we do the cold work. Now, the time at which this happens is dependent on what you start with, how much cold work you add, what material it is. How long this recrystallization process takes isn't standardized. If you use this application, you'd have to figure this out. You'd have to do some experiments for your material to determine what time is this, how many hours, how many seconds, how many minutes. Of course, that depends on the temperature you're using. So let's say your supervisor says, okay, this is what we're going to do. We are going to recrystallize this metal for this application. I have no idea what temperature to use or how long. I need you to find out. How would you do that? How would you know what temperature to use, how much cold work to use, what temperature to use, and for how long? All right, well, let's think about this whole process. I want to end up with more grains, right? I want to end up with more small grains. How does the percent cold work affect the number of grains I'm going to end up with in the end? me say this in a different way. Here's one example of what happened. Let's say at this step, I add more cold work than at this time. If I add more cold work, this is the same, this is different. What will be different here if I had more cold work to start? If you have a guess and you just don't want to say, Ella.
Will there be more high energy locations?
If I have more cold work, there's going to be more places for grains to form. So I'm going to have more, a higher in number, new grains. If I have a higher in number new grains there, I'll have a higher in number of new grains here. And then the result will be more strengthening or less. If I have more grains, what happens to the grain boundary? I have more grain boundary. So I have more increased strength. So how much cold work? As percent cold work increases, the number of new grains that are nucleated increases. So the final grain size decreases because I have more grains. So there's more grain boundaries. Would there be a limit to how much more cold work I do in this step? Is there a bad outcome as I increase the amount of cold work? Well, if I want to preserve it in one piece, yeah. So there's a limit to how much cold work I can put in there as far as the integrity of the part that I have. The increase in strength with grain boundary area also has an upper limit. It has a big effect for small decrease in grain boundary, or small increase in grain boundary area, but it levels off. And so this has an upper practical limit. But probably I'd like to get close to it, because here's a way that I can really increase the strength with this process. So how much cold work? Well, I'm going to try to figure out how much more I can add. How much more cold work can I get? I'll do that at the beginning, just knowing if I go more than 40% cold work, it starts to break. Okay, I'm not going to go more than that. Maybe I'll go 35. And I'll revisit that later. All right, what temperature should I use? If I increase this temperature, how do you expect this to change? The higher this temperature, the faster this will all go. Yeah? Well, going faster probably is really great, as long as I can control what's happening. So the temperature affects the duration. I want a duration that I can manage. I mean, if I use a temperature where all of this happens in 10 minutes, that might not be so great, because I can't stop it at the right moment. So I'm going to choose a temperature so that I have a duration so that I can know exactly when this happens and take it out of the furnace at that time. So then the last question is, how will I know when that time is? How will I know when recrystallization is actually over? What could I do? Well, that's the experiment. Once you decide on a percent cold work, then you choose a temperature where you can actually manage this, and then you take the piece out at varying times. So I take this piece of metal, I apply a certain amount of cold work to it, and I cut it up in pieces. And I put all the pieces in a furnace at a given temperature. And I take them out at intervals. And I measure their hardness. So what would happen? Well, as it's in the furnace, probably going to start out with a pretty high hardness because I've done all that cold work. Recovery, there's going to be a reasonably noticeable drop in hardness. Let's call it this. That's recovery. And maybe it doesn't happen in 1 second. And then during recrystallization, it's going to stay relatively constant, but it will drop during recrystallization. And when recrystallization is over, then it drops at a higher rate. This is hardness. And this is time at some particular temperature. If I go at a lower temperature, this goes longer, it's easier to see maybe when that happens. But if I go too short a temperature, I might have a hard time seeing the change. So I'm going to take out a bunch of pieces and I'm going to take them out at various times. And I'm going to plot the hardness at each of those times. And when recrystallization is started, I'll start to see a bigger drop. Now I know my recrystallization time. Questions? This kind of strengthening mechanism doesn't have a lot of math to it because there's so many factors here. Composition of the metal, the way in which you apply cold work, the extent of cold work, the temperature that you use, the there's one other, but I think you get my drift. There's a multi-factor equation that you might be able to create where you can input all of those variables and predict recrystallization time. Or you could just do it the old-fashioned way, like they've been doing, since King Arthur, and just test until you find it. Okay? So, this ends part 1 of this class. Part 1 of this class being, I should say part 1 of the metallurgy part of this class. Part 1 being the ways to strengthen metals that are single phase. What would it mean to have a metal that's 2 phases? That's what we're going to start talking about. So there are metals that are actually, within the metal, 2 different solids. And they're distributed in different ways. They each have a different composition. They each have a different crystal structure. And the way that we distribute one into the other, the harder one into the softer one, determines the strength. And the one that, is the biggest example is steel. Steel, room temperature steel has two phases. One is mostly iron, one is iron with carbon. Two different phases. If we took a piece of steel and we polished it and we add some kind of a corrosive agent so that it just starts to corrode on the surface, and we then get rid of that and we look at it under the microscope, that corrosive material, whatever it is, it's called an etchant, will have etched those two different phases differently, and we'll be able to see them. And we'll be able to use heat treatment to change their distribution. All right? So, let's take a break, and then I want to try an experiment with numbers. Okay, so take a 5-minute break. I'll put the numbers up here, and let's see if we can come up with something. Oh, I wish I could do the probe. I can't do the probe. But, oh, I think it has to do with, many years of being, the word, dominated by another party and another country. Like, I kind of know a lot of places that have been dominated by another country, and they haven't figured this out. It's my very, very favorite place. Okay, so there's an experiment. Got some nickel copper. Take some pure nickel, all right? Pure nickel, get it to the liquid state, above 1500 degrees C, and you cool it down. That's the black line here. Cool it down, and we've got a thermocouple that's keeping track of the temperature over time, right? So we're cooling it down, seems to be a constant rate, and we get to 1085 C, and it stays at constant temperature for a while. And then, after a while, it starts cooling again. What's happening here? Why is it not cooling any further here? Where are the chemical engineers? What's happening?
Changing state. So it's
Changing state, right, it's solidifying here. So all the energy is being used up and going from liquid to solid state. So this would be the melting temperature of nickel. That's one way that we could calculate or experiment to find the melting temperature of liquid. So here is the melting temperature of liquid. T, that's not of liquid, T sub M for nickel. Oh wait, that's 0% nickel. So this is all copper. Melting temperature for all copper, yeah, that makes sense. If we have all nickel and we cool, we get to 1460, I think, and then it stays constant. That's a melting temperature for nickel. Well, what would be the melting temperature then of 50/50? Well, it's 50/50, so it doesn't have one distinct melting temperature. If I have a 50% nickel, 50% copper liquid, and I cool it, I'll get to about 1350 or so, and then this will just change slope until I get down to right around 1300, and then this will just change slope again. So, all nickel, this is liquid. This is liquid plus solid at one temperature. This is solid. For all copper, this is liquid. To get to this melting temperature, we'll have liquid and solid together, and then we'll have all solid. If we take a 50/50 mixture, we'll have all liquid will have liquid and solid over a range of temperatures. And then all solid. That's interesting. How could we represent this on some kind of a chart or a graph? If I wanted to be able to choose a concentration of nickel and predict that range of temperatures, how could I present that on a graph? Well, so my experiment, I'm cooling, and I'm noting at what point there's a phase change. At what time there's a phase change, or at what temperature there's a phase change. So what is my independent variable in this experiment? What is the thing I'm controlling?
Percent nickel.
Say what?
Percent nickel.
Right. I'm controlling the percent nickel, and then I'm measuring at what temperature it changes state. That would be the dependent variable. If I'm going to plot this, which axis do I use for the dependent variable? Y or X? Jack says Y. Anybody agree with Jack? Always. If there is a dependent variable, it's always the y-axis. Okay? So if I'm going to make a graph here, I'm going to have on my x-axis the weight percent nickel. And my y-axis is going to be the temperature at which these things change phase, temperature. And I need to be able to go from, looks like 1,000 to 1,500. Got 50%, 100%, and 0%. Notice, I don't have to tell you what weight percent copper there is, because they add up to 100. Okay. So for my 100% nickel, my 100% nickel had this change of state, this melting temperature at 100% nickel at 1455 C. So at this composition, I have liquid and then solid. And this is the melting temperature for nickel, which is 1455. And if I do the same for copper, melting temperature, I'm just so lucky here. This is a melting temperature of 1085 for copper. Right there. Above that liquid, below that solid. All right, now I did this experiment with 50-50. And as I was cooling, I had all liquid until 1320. See? And then I had liquid plus solid until 1260. So liquid plus solid, liquid, solid. I'm going to take these temperatures off. It's going to get too cluttered. All right, well, let's look at the 25 and the 75. What's made up here? So all 0% nickel, all copper, above 1085 is liquid. Below 1085 is solid. And they have both at 1085. For my 100%, it was 1455. And the 50/50 was all liquid above 1320, both phases 1260 to 1320, and below 1260 is solid. So, well, let's fill this in, we're thinking. Let's do the 25 and the 75. So at 25% by weight, nickel, above 1210 is liquid, and below 1180 is solid, and in between them is both phases. And at 75, above 1380, and below 1350. All right. So for my 25, it's 1210 and 1180. 1210 and 1180. And for 75, 1350 and 1380. 1350 and 1380. And I could add the others in here, but ultimately, what I'm building is called a phase diagram. Sort of a map that says anything above this line is liquid. This line is called the liquidus. And anything below this line is solid. And this line is called the solidus. And in between, I have both phases. And some think of this as a map. If I told you the composition and temperature of a nickel copper alloy, you would be able to tell me, is it liquid, is it solid, is it both? And you would also be able to tell me something else, which this data hasn't shown us, but is kind of handy. And that is, if you're in a place where there's both liquid and solid, you would be able to tell me the composition of each of those phases. And so, but in order to talk about manipulating the two phases in order to strengthen a metal, we have to be able to know what phases there are. We have to know what temperature and composition I should be at in order to have the phases I need. And so that's why we start talking about two-phase or multi-phase solids by constructing and then working with these maps called phase diagrams. Now this particular phase diagram for copper and nickel is unique because there's only one solid. You're like, well, of course there's only one solid. There's only one solid. Most metals, there are two or more solid phases, and the difference between them is their crystal structure. But copper nickel is an isomorphous system, meaning same shape or same crystal structure in the solid. There's only one solid. Much more typically, a phase diagram will look, the simplest of phase diagrams will look kind of like this. OL, there's not a element OL. Oh, I'm pretty sure there's not an OL. But I think there is. Is there an LE? I don't think there's an LE. Okay, so we're going to have the olivium-lexium phase diagram. All right? And this is going to be weight percent olivium. Unfortunately, lexium doesn't even show up here, but we know it's there. And I'm using this because I don't want to, I don't want to use an actual system and get the temperatures wrong. So this is just a hypothetical phase diagram, but this is what often a phase diagram will look like. Or one example. So in this phase diagram, this is liquid, this is solid 1 alpha and solid 2 beta. So alpha and beta are two unique solid phases. They are not soluble in one another. So what did it take to be soluble? You had to have the same crystal structure, you had to have a similar radius, and similar vacancies. So these are not the same crystal structure, and they might not be the same of the others. Two unique solid phases. Alpha is rich in lexium, and beta is rich in olivium. And between each of these solid phases is a two-phase region. Just like here, between the liquid and the solid, there's a two-phase region. Here, there's a two-phase. So in this region, I have alpha plus liquid. And here I have beta plus liquid. And all of this area, alpha plus beta. And alpha and beta are both solid, but they have different compositions, and they have different crystal structures. So alpha and beta are these solid phases. OL and LE are elements, are components. And typically they're elements. They might be compounds. And so my x-axis gives me the weight percentage of one of the two components. Now, why doesn't it say percent Olivia instead of weight percent Olivia? Couldn't it be the same thing? Well, if Olivium and Lexium have the same atomic weight, yeah, percent of one would be the same as weight percent of one. But let's say Olivium has an atomic weight of 25 grams per mole, and Lexium has an atomic weight of 10 grams per mole. So every 2.5 atoms of Olivium, well, I don't want to do this in my head. If I said it's 50% Olivium by weight, that's different than saying it's 50% Olivium by atom, right? Sometimes you'll see a phase diagram that'll have up here on top the atomic percent, and it won't be linear. I just want to make a point that you have to use weight percent when you're describing the amount of a component. You can't just say percent. All right, so let's talk about this particular phase diagram. This phase diagram is, well, as this one's called an isomorphous. This phase diagram is called a eutectic phase diagram. And eutectic means that there's a transformation at a unique temperature and composition where a liquid transforms to two different solids at one temperature, at one composition. So that looks like it's at about, we'll call that 35. That point right there. And we'll say this point is 18. We'll say this point is 77. So I've taken that line that starts at 18 weight% OL, and it has this meeting place of 35, and it has this endpoint at 77. So for this phase diagram, that eutectic transformation is right here. Liquid at 35 weight% nickel. When it's cooled through, let's call this So that might be 775. So liquid at 35 weight percent nickel, when it's cooled through 775 degrees C, transforms to alpha, that's solid one, that has 18 weight percent nickel, plus beta, that has 77 weight percent nickel. So that, for that phase diagram, that's the eutectic reaction or eutectic transformation. It's sometimes called either one. But note that I have a liquid that's transforming into two different solids, all at one temperature. All of that's happening at one temperature. What does it look like? Well, if I were able to look at this under a microscope, I have liquid, I can't see anything under the microscope, but at some point, a little bit of beta forms somewhere. A little bit of beta. We'll let beta be black. And when beta forms, it has to take some olivinium away from the environment because it's higher in olivinium. And so in doing that, it's creating areas of lexium next to it. And so, let's say as it's growing away from the wall, there's a layer of olivinium, and then there's a layer of lexium, and there's another olivinium, and there's another olivinium. And what it is layers of the two phases. And maybe just so that we don't worry about which one is it? We'll make lexium be red. And that just grows into the solid, forming this striped, layered structure that is our equilibrium microstructure, our eutectic microstructure. Layers of black, layers of olivinium and lexium. That's this kind of phase diagram. It has an eutectic. There are phase diagrams that has multiple eutectics and other transformations, but we're not going to get into those right now. What I want to do lastly is just talk about what we can get from this phase diagram, or any phase diagram. answers three questions, answers some more, but for now, we're gonna look at these three. What phases are present? What's the composition of each phase present? And note, the answer will be in weight percent of the moment. What is the relative amount of each phase? This is, the answer will be in percent, not weight percent, of a phase. So, for example, we'll use this phase diagram that we've got. And we'll answer this question at a couple points. So let's do this at right there. And well, let's do it right there. So this will be point 1 and point 2. I'll just do the example of calculating those three things at those two different points. Okay, so point 1 is, these are both, we're going to say at we'll say 14 weight percent OL. Those are both of these points. And this one, 900. And this one, 600. So I said, I've given composition and temperature. There's my composition. Now my composition, 14 weight percent. Oh, that's right. 14 weight percent OL. That's my composition. Temperature 900 C. First question. What are the phases present? That's the easiest question. We just look where we are on this map. In what region are we? Well, we're in the region where there's alpha and liquid. Notice I'm not saying solid and liquid anymore because there's more than one solid. I'm going to just sort of reproduce that over here. So this was 14. And I need to draw a line across. And note where where the endpoints are. So I'm gonna say that's 14, I'm gonna say this is 6. And this is 20. So I just reproduced it here. This is 6 and 20. Then we are in the liquid plus alpha region. Over here, on this side, this is the alpha area. Over here, this is the liquid area. Right? So question B or 2. What is the composition of each phase? So I got alpha and liquid, and I need to figure out what is the composition of each phase. That's why I drew this line, and I figured out what this value and that value was. Where I cross this line with alpha, that's 6, that's the composition of the alpha. So alpha is 6 weight percent nickel. That 6 comes from here. And the liquid has a composition of 20. So notice, the answer to the second question about composition has to be in terms of weight percent, and it is. Okay, the last question is, what's the relative amount of each phase? And to solve that, we need to take this part out and draw it. So I've got this length that goes from 6 to 20, and I'm at 14 there. And this 6 is alpha, this 20 is liquid. 14 is what my alloy is, and it's kind of like, we'll say it's kind of like a fulcrum. So the percent alpha is equal to, this is called the lever rule for a reason, because we're going to take the length on the opposite side of the lever from where alpha is. So there's alpha. We're going to want this length. I'll call this L2, and I'll call this L1. So the percent alpha is L2 over the total L2 plus L1. And the percent liquid is L1 over L1 plus L2. Now, unfortunately, you're really smart and you're going to make some mental leaps and you're going to think you get it, but you're going to flip it and then you're going to make a mistake. So take another look at this. The percent of this thing is a function of that length on the opposite side. And the percent of this thing is a function of the opposite length. So the percent alpha I could say is 20 minus 14 over 20 minus 6. The opposite side, 20 minus 14, over the total length, 20 minus 6. And the percent liquid is 14 minus 6 over 20 minus 6. And they add up to 100%. So theoretically, you don't have to calculate both. You calculate one and then subtract it from 100%, assuming that you haven't made any math error. They should add up to 100%. So 6 over 14, something just under 50%, I don't know, 45 or something. Do you follow me? So let's real quick do the same thing at 600 degrees. 14 weight percent, aluminum at 600. So now we're here. We're in the alpha and beta region. And our line goes from there all the way across to there. So I've got alpha and beta. And the alpha has we'll say 4. And the beta has 100 weight percent. Oh no. Straight from the top. And then for C, my lever goes from 4 to 100. I'm at 14. 4 is alpha, 100 is beta. So the percent alpha is 100 minus 14 over 100 minus 4. And the percent beta is 14 minus 4 over 100 minus 4. And we're going to do a lot of that calculation for a while. So make sure you've got that flip there in your head, right? We'll pick up with more eutectic phase diagram next time, which is Tuesday, which is the only day we're meeting next week. And which is when homework 5 is due.
Is that due online?
No, I would really prefer that you don't turn it in online. The drawback of you turning it in online is I cannot show you what's wrong. I can just give you a score. And I'd much prefer it if you turn it in and I can write on your sheet what's wrong.
Do you want to print it out on that handout?
That'd be great, but if you can't do that, just make sure it's neat enough for me to find your